don't have to tell you much about the group. You just did that in the summary, but I brought with me some folks from the group. And this talk, I'm going to do things a little bit differently. So I'm highlighting here, this group picture is most of the people in the group, and showing you some circles around the faces of the people that I brought here with me. From left to right, we have Philippos, then Yorgos, Lucas, Sean, and Arash. If you want to show your videos, I don't know if you've got your videos switched on, but if not, please do. And what I'll be doing is, rather than using up the whole hour myself and telling you about all the cool stuff we're doing, which is the standard protocol, and then claiming all the credit, basically, I thought this time I would actually hand over some of the time to the actual folks who were doing most of the work, and allow them to make some connections with you as well, which I think would be great. So what I'll be doing is spend a few minutes to tell you about, broadly give you a broader overview of some of the work that we're doing, and then I'll hand over to the folks I've brought with me to tell you about some projects that we had published in papers last year and this year. Okay, with that said, I'm going to get started. So we are the Autonomous Agents Research Group, and broadly speaking, our research goal is to create autonomous agents which can accomplish tasks in complex dynamic environments. And I'm showing you here 3 examples of the kinds of applications and problems that we like to think about. For example, on the left, you have a large warehouse that is being managed by a swarm of robots that need to collaborate in one way or another. In the center, you have a vehicle that is driving in an urban environment and needs to interact with the other vehicles. And on the right, you have a classic RoboCop software example. And what all these applications have in common is that there is multiple actors that need to interact in some way to achieve their goals. And these goals might be perfectly aligned, or they might be in competition, or somewhere in between. So we have a strong focus on problems where there are multiple actors that in fact have to work together or interact in one way or another. And I feel this is a very rich problem space. There's a lot of really interesting technical problems in multi-agent systems research. Just to bring everyone on the same page, so we model these problems as multi-agent systems, and I'm sure most of you already know what this is, but just in case, maybe if we have new folks here to this area, and also to make sure that everyone is on the same page, let me just give you the rough outline. So a multi-agent system begins with a shared environment. There is some description of an environment, which could be a physical environment, or it could be a software-defined environment. For example, a physical warehouse or a software sort of gaming environment. And within this environment, we have the agents. So they're shown here as the squares. Every agent has some means to sense what's happening in the environment. So to receive information about the state of the environment, every agent then has some means to affect the environment state through actions. And in particular, the agents have goals. And what makes these problems so interesting and challenging is the way in which the agents have to coordinate their action choices in order to achieve these goals. So this could be to drive the system state into a target state, or to maximize some objective function. So this is a general description of a multi-agent system, and I like to introduce this because it's a nice tool to describe some of the research agendas. So that we work in. So here I'm going to give you basically the 2 main categories of the types of research domains that we're working in. The first one is when we control one agent in a multi-agent system, and the other agents may be controlled by other organizations. We don't know ahead of time who they are and what their policies are. So in the picture, I'm showing you one blue square, which is us, and then the other squares are controlled by someone else. And the question is, how can our agent learn to collaborate effectively with these other unknown agents? And so there's a range of exciting questions that go into this space. Problems such as the ability to, or how to recognize the goals and intentions of other actors in the environment, how to make predictions about their future actions or trajectories, how to integrate prediction with decision-making and planning, and also developing systems in a way that allows us to make sense of those choices and predictions by being transparent, interpretable, even allow for strict verification in some cases. And so this is one of the main research lines that we're working in. And there's also a major application in the space, which is autonomous driving. So in the introduction, it was already mentioned that I also work with a UK-based company called 5AI, where we basically developed the whole technology stack from A to Z to develop autonomous driving. We were recently acquired by Bosch, which was a big deal, and now we are the largest group in Europe operating in the sector. And basically, all of the problems that I'm mentioning here on the slide also feature in this. And then on top of that, you have all the other technological problems and integration. And we were running large trials in London as well, and by far the most sophisticated urban road trials that have been conducted in Europe to this point. So this is a really exciting transfer application for some of the work that we do. The second major line of work that we do is when you now control all of the agents. So I'm highlighting all the boxes in blue now, which means that we control all of them. And the question here is, how can the agents collectively learn to solve a problem that they're given in this shared environment? And so in particular, this will be grounded in multi-agent reinforcement learning, which is one of the types of approaches that we specialize in heavily in this group. The questions that appear here is how to coordinate and communicate, and how to learn coordination and communication. We're also interested in how to scale these approaches to many agents through mechanisms such as parameter sharing. We're interested in problems where there is dynamic team composition, so agents entering and leaving of an agent may have diverse types and interests. And also more recently, we're looking at really challenging problems where we're training a team to solve one task and see how that team can transfer to a different task and adapt its teamwork strategy. So lots of exciting work in this space. And again, there's a major application that we are working on in this space, which is warehouse order picking and intralogistics. So here we're working very closely with a very large global player in this field called Dematic, which themselves belong to Kion. And we are looking at how to integrate multi-agent reinforcement learning in these robot fleets and how they interact with human co-workers in these spaces to optimally manage these warehouses. So a really exciting transfer application again. Right, so these are the two main categories or main paradigms that we operate in, and all these various questions come up here. The next step in the presentation will be for me to hand over to the different people that I brought with me. But before I do that, and while I still have your attention, I just want to bring up one more slide to give you some general resources for people interested in multi-agent reinforcement learning, which I think is the big theme here. There's a few things that I think you guys may want to check out. One is we have a blog on our research group web page. You can see the URL here. And there's a few blog posts that have come out, which I think could be of interest. For example, we have a blog post that recently came out on reinforcement learning implementation tips and tricks that we like to use. And there's quite a few things that go in there. I'm sure you would be aware that sometimes these implementation tricks do not come across in papers, but make a really big difference. And if you're new in the space, I think if you're new in this space, this will help you bootstrap, I think, a bit more quickly. There's also a blog post about some inaccuracies that we've observed in multi-agent systems, multi-agent RL research that I think need to be corrected. So check out that post. There's a post about multi-agent learning environments where we collected a whole bunch. And just yesterday, we released a brand new post where we talk about a multi-agent RL coding platform or a code base called ePyramid that was released last year in NERVs. So please check it out, and I hope this will be useful to you. The second thing I want to bring up is that we have a code repository which is keeps growing, has over 20 active code repositories at the moment, including a large code base for ePyramid, which is for people who are developing multi-agent RL algorithms. It's itself based on Pyramid, but extends it in all kinds of directions to make it more flexible and more usable. And it's already been used quite a bit, I think, in the community. So if you haven't heard of it, please do check it out and let us know if you feel that any features are missing or if you encounter any issues. And lastly, I also want to announce that we have been working on a book in multi-agent RL. This is an introduction textbook, which is currently under review with MIT Press. And it's nearly complete. We're hoping to have this released closer to the end of the year. And still working on it, but it's shaping up nicely. If you want to get updates about any of this material, and in particular find out when the book is released, please follow us on Twitter. You see the handle down here, and then you get the updates for that. Right, so that's my part of the presentation. Now I'm going to hand over to the first paper presentation, which will be done by Arash, and this is a paper that came out last year at ICML. Okay, Arash, I think you can take over now.
Okay, thank you, Stefano. So hi, everyone. So for the first work that I'm going to present today, I'm going to present our work that has been published in ICML 2021 last year. And this work is also done under the ONR research grant. Okay, the main goal of this work is to solve the open ad hoc teamwork problem. My slide sharing thing doesn't work, I think. Okay, so sorry about
that. It's working for me. I can see your slides changing.
Okay. So the main goal of our work is to solve the open ad hoc teamwork problem. Now, the ad hoc teamwork problem itself refers to this specific problem that Stefano has alluded to before, where essentially we assume control over a single agent, which then needs to learn how to collaborate with different types of teammates with unknown policies in a particular environment. Now, open ad hoc teamwork itself refers to a specific instantiation of the ad hoc teamwork problem in open multi-agent systems. Now, open multi-agent systems are characterized by how agents may enter or leave the environment anytime. Thus, as a result, in open ad hoc teamwork, the number of agents inside the environment may change in between time steps as a result of agents entering or leaving the environment. Furthermore, in open ad hoc teamwork, we also assume that agents that are entering the environment may assume different types, or basically different ways of deciding their actions in order to behave in the particular environment that it is currently operating in. Now, based on these characteristics of open ad hoc teamwork, whenever it comes to solving open ad hoc teamwork, essentially we require a policy that can adapt the learner's behavior so that it could then adaptively change its behavior against all the different types of sets of teammates that it encounters in the environment. Now, for an example of an open ad hoc teamwork problem, consider the problem of designing a robot that needs to perform in pickup robot soccer as an example. In this particular example, the set of teammates that the learner is going to be interacting with changes as a result of things like player substitutions or maybe red cards. And as a result of that, this robot will need to change its behavior accordingly to these different partners that it encounters. Now, for our solution for solving open ad hoc teamwork, we essentially use graph neural networks, which we then subsequently train with deep reinforcement learning to then estimate the optimal action values of the learning agents. Now, the reason why we use graph neural networks is twofold. First, because graph neural networks are permutationally invariant, so it means that essentially no matter what ordering you present the agents into the model, essentially the output is the same. And this is like a very useful property that you could use for open ad hoc teamwork, while on the other hand, GNNs have been proven to be effective in handling observations or inputs with varying sizes in other related research areas like multi-agent RL, or maybe in supervised learning in general. So as a result, we use GNNs here, and in particular, we use GNNs to learn the impact of all other teammates' actions towards the learner, and at the same time, we also use GNNs to predict the likelihood of all other agents' actions. Now, before I go into more details about how we use our GNNs, I'll just mention how we actually pre-process the state information that we then provide into the GNNs. And in this particular case, we basically assume that every agent in the environment will be abstracted by the node inside the graph structure that is going to be provided into the GNN. So each node will be corresponding into like one agent, and at the same time, each node will be associated with a node feature, which will then be associated with a feature related to a particular agent that it is currently representing. So under this particular case, whenever we need to change the number of agents inside the environment due to the openness of the environment, what happens here is that we just need to change the graph structure that we input to the GNN. Basically, let's say here, if you substitute one agent with another agent, you then substitute the node associated to one agent with the node associated to this new agent that is entering the environment. Now, for our solution for solving open ad hoc teamwork, this is the specifics of it. It's basically called graph-based policy learning, or it is shortened as GPL. In general, the computation of the action value function in GPL undergoes 3 different processes. The first process, it doesn't involve any GNNs at all. And this process is computing the types of the teammates that the learner is interacting with. And this is particularly important because the teammate types informs how they behave currently and in the future. And as a result, it affects the returns that the learner will experience in the future. However, teammates' inherent types, as I mentioned before, are inherently unknown. So we need to infer them based on the trajectories that are displayed by each agent. Now, using the types that are inferred from these networks based on the trajectories of the agents, use the type inferred by the model into 2 types of model. And these models are all represented as GNNs. The first model is the joint action value model. And the function of the joint action value model is to predict the effects of all agents' actions towards the learner. I won't go into more details about why we use the joint action value model instead of directly estimating the action value function of the learner. But essentially, if you read the full paper, it helps with credit assignment. On the other hand, the agent model helps us to use the joint action value model to then compute the action value function. Because without that, you can't actually compute the action value function directly from the joint action value function. Now, the final step of the action value computation, like I mentioned, is basically combining the outputs of the joint action value model and the agent model. And the way you combine this is through a marginalization process. And overall, all of these components can be trained end-to-end using reinforcement learning, and that's for the joint action value model. And on the other hand, you also use supervised learning to train the agent model, which essentially functions as a predictor of the behavior of all other agents inside the environment. Okay, so based on this, we tested our approach in 3 different environments. The first environment is level-based foraging. The second one is Wolfpack. And the final one is Fort Attack. LBF and Wolfpack are pretty similar. In a sense, the goal of the agent here is to collect objects. On the other hand, in Fort Attack, it's a little bit more difficult because essentially the goal here is for the learner to protect a certain region here from the attack of other agents. So essentially in Fort Attack, we have the presence of enemies that we need to fend off. Now, for the results, we train GPL alongside with several baselines in all these 3 environments under this particular setup. So we assume that we have like an open ad hoc teamwork problem. So we define an open process that essentially changes the number of agents inside the environment. However, during training, we limit the number of agents up to maximum 3 agents for any given time step. And then we basically train all the methods under this particular setup in all these 3 environments. Now, in our experiments, we compare GPL against 2 types of baselines. The first type of baseline is baseline based on multi-agent RL. And the thing that we want to see here is whether multi-agent RL algorithms are actually a good fit for open ad hoc teamwork. On the other hand, we also compare GPL against different ablations of GPL to highlight the usefulness of the different components that we have defined in GPL. Now, the 2 different multi-agent RL algorithms that we compare GPL against are MADDPG and DGN. And the results in all these 3 environments pretty much indicated that all multi-agent reinforcement learning algorithms perform the worst in open ad hoc teamwork compared to any other baselines, and including compared to GPL. And this is because in multi-agent RL, what you do is essentially you train the agents to be good when performing against other jointly trained agents that you see during multi-agent RL training. But when you're dealing with agents that you have not seen before, as what you need in open ad hoc teamwork, essentially the generalization performance of multi-agent RL algorithms will degenerate in this particular case. On the other hand, we also see that in all three environments, GPL performs much better than these ablations, which basically only differs in the architecture that are being used and also in how they use the agent modeling technique. So this basically means that GNN's usage of GPL's usage of GNN and also its usage of the agent model is actually providing this jump in performance. Now, finally, we also test GPL in a generalization setup. So the question that we want to find out here is, how does GPL perform when it is working on an open process that it has not experienced before during training? And to test this, what happens is we actually test GPL against an open process that has more agents now. So previously in training, we only see 3 agents. Now in generalization, we see up to 5 agents. And this kind of open process, it hasn't been experienced before by the algorithms. Now, in general, it's not surprising in some environments that GPL outperforms other baselines in this particular setup, mainly because during training, GPL already outperforms them. So it is expected for it to perform better during generalization. But interestingly, for LBF, where GPL does not outperform, but actually performs similarly with other baselines in terms of training, it turns out during generalization, GPL still outperforms these other baselines when it comes to generalization performance. So that means that GPL's architecture and also how it uses its components turns out to be useful for generalization too. Okay, and that's pretty much it for me. For more information about this work, you can find this in our full paper, and you could also find details about the code here in this particular link. But before I hand over this presentation to the next presenter, I'd like to highlight that our group is also organizing a workshop in ad hoc teamwork at ICHCAI 2022. For those of you who are interested in topics related to ad hoc teamwork, such as zero-shot coordination, adaptive learning agents, or agent modeling, this could be an interesting workshop that you could attend. Now, for full information about this workshop, you could find it in this particular link. And yeah, I'll hand it over to the next presenter then.
Okay. Hello, everyone. So now I'm going to present our work, benchmarking multi-agent deep reinforcement learning algorithms in cooperative tasks. This work was presented in NeurIPS 2021 in the track on datasets and benchmarks. So first, let's start with some introduction motivation behind this work. In general, in multi-agent reinforcement learning, we have lack of commonly used benchmarking environments. Many authors in the papers tend to change the environments to make them focus on specific difficulty. Additionally, we have lack of consistent algorithm implementation, and this is very common even in single-agent reinforcement learning. And as a result, it is difficult to measure the progress that's achieved in model research. For this reason, in this paper, we tried to benchmark 9 model algorithms in 5 environments that define in total 25 different cooperative tasks. We only focus on cooperative environments. We open sourced 2 new evaluation environments for future multi-agent research. And we also open source the PyML code base, which extends the existing PyML code base to include more algorithms, compatibility with more environments, and flexibility with implementation details. So first, let's see the algorithms that we evaluated as part of this work. The algorithms belong in general in 3 categories. The first one is independent learners. So here we have 3 algorithms: independent pre-learning, independent advantage actor critic, and independent proximal policy optimization. These, in general, independent learning, each agent is using a reinforcement learning algorithm to learn and completely ignores the presence of the other agents in the environment. Then the other 2 categories that we have, in general, fall under the paradigm of centralized training, decentralized execution, which practically means that during training, we assume that we have access to the trajectory of all agents and we use them for training. But during execution, each agent selects its actions based on its own trajectory only. So the first category under this paradigm is the centralized policy gradient methods, which are actually actor-critic methods. The actor is fully decentralized in the sense that it's conditioned only on the trajectory of its agent, and the critic, which is utilized during only training, is conditioned on the joint trajectory of all agents. By condition on the trajectory of all agents, it's able to learn better representation of the state value or the state action value function, and which helps a lot achieve better performance. And finally, the last category, which is also under this paradigm, is the value decomposition methods. Here we evaluated two methods, value decomposition networks and Q-mix. Basically, these methods try to decompose the joint Q value into individual Q values for each agent. And these are two of the most famous methods, but there are several extensions of these methods as well. Then all these algorithms are, you can find all these algorithms in the ePymal code base. In general, ePymal code base is an extension of the existing Pymal code base. And the reason is that Pymal in general lacks several actor critical algorithms such as IA2C, MADDPG, MAPPO, and others. Most of the implementation details are fixed. For example, Pymal assumes that the parameters between the agents are shared. The update of the target networks in value-based algorithms are hard always. The agents always use RNNs. And we believe that having the ability to actually change this, manipulate these implementation details easily is very important in order to optimize our algorithms. And finally, it is also compatible with the Starcraft multi-agent challenge, at least the original Pymal repository. For this reason, we open source ePymal, which addresses most of these concerns. And you can find the link to the code here and a blog which explains how to install, execute experiments using ePymal and how you can actually use ePymal to write, to implement new algorithms. Then we have our evaluation environments. We have 5 different environments. On the top left, we have 2 matrix games. On the left is the climbing game, and on the right, we have the penalty game, where you can use different values of K, negative values, to define different tasks. On the top right, we have the multi-agent particle environment, which consists of several two-dimensional navigation tasks and was released from OpenAI. On the bottom left, we have the Starcraft multi-agent challenge, which consists of several tasks where we control a team of agents which competes against another team of agents which is controlled by some predefined AI. On the bottom middle and bottom right, you have the 2 environments that we open source as part of this work, the level-based foraging and the multi-robot warehouse that I'm going to explain next. Okay, so this is the level-based foraging environment. It's a grid world. Oh, sorry. Take some time. Okay, it's a grid world which consists of several agents and food items. At the beginning of the episode, the agents and the food items are randomly spread in this grid world. The agents and the food items have a specific level, and an agent can only gather a food item if its level is equal or greater than the food's level. And agents have to cooperate together to load simultaneously foods of higher level. As for example, you can see in the third figure, where there's an item, a food item of level 4. Both agents have to simultaneously try to load it in order to gather one. And the goal here for the agents is to gather all available foods in the environment. Then we have the, take some time to change.
It's working for me, Yorgos. I can see the changes. Now we're on the plot slide.
Oh, really? It takes a lot of time for me. I don't know. Is that my connection?
Now we're on the.
Yeah, I wasn't getting it. I just see that.
Ah, now we're in the
Now
correct, the
now we're on
multi-robot
the-
warehouse.
Right there.
Nice. That's where we're supposed to be. So the multi-robot warehouse, again, it's a grid world which consists of several agents. The agents receive a request for a shelf, and they have to go grab the shelf and return that to the goal location. Then they have to return the self in an empty self space in order to leave that, and then receive the next request to go grab the next self. In general, this environment focuses mainly on sparse reward because there are several time steps after which the agents receive the reward. Also, the environment is partially observable because each agent can observe up to one grid cell in each direction. So it's a really challenging environment. Then finally, we present some evaluation returns. So here we present the average evaluation returns of all algorithms, average over all tasks within an environment. So practically, we go in each task, for example, the multi-agent particle environment, and we normalize the return in the 0-1 range for all algorithms, and then we take the average over all tasks, and we also present the confidence intervals. So in general, we can see that QMix performs the best in the multi-agent particle environment. In SMAC, MAPPO and VDN tends to perform the best. In the level-based foraging, we see that the A to C based algorithms such as IA to C and MA to C are the best ones. And in the warehouse, we have the PPO based algorithms to perform the best. So in general, we see that there's no some algorithms that they always win. And one of the best algorithms that we have here and is constantly performing well is MAPPO. And I think some people from this group are also part of this paper. And so to sum up, we benchmark and compare 9 MARL algorithms to 25 cooperative tasks. We open source 2 multi-agent environments for multi-agent research, and we open source PyMARL, where you can find the link to the code below. Thank you.
Okay, hi everyone. I'm Philip, and I have a few slides to present about our paper, which was at NeurIPS 2020, and it was called Shared Experience Actor Critic for Multi-Agent Reinforcement Learning. So, first of all, just to get back into the same page, we are in the multi-agent reinforcement learning setting where all agents are learning concurrently. So everyone collects experience and learns from it, and everyone starts from scratch. So to introduce the idea, first, I'm showing here 2 ways that the researchers have typically used to assign policies to agents. On the left, we have no parameter sharing, where each agent has its own policy. And on the right, I have parameter sharing, where all agents share the same policy. So all agents have one set of parameters, they update it, they collect experience using it, and in the end, they get a copy of it to just execute in a decentralized way. So both of these methods have advantages and disadvantages. And first of all, I'm using here something like a spectrum. It's more like a spectrum of choices. It's not like you can linearly move from one to the other, but it's a spectrum of choices, and we have some algorithms here to populate this this space. So no parameter sharing has the advantage that it allows for distinct behaviors to be learned. So each agent can just learn totally different things from other agents if it has to. However, agents only learn from their own exploration. If some other agent does something good, our agent, so agent number 1, wouldn't learn about it or have a way to update its network using that experience. It's also the case that the number of parameters scales linearly with the number of agents. So if you have like hundreds of agents, that becomes very hard computationally because we have 100 neural networks essentially. Parameter sharing, on the other hand, has exactly kind of the opposite problems and advantages as well. First of all, it's sample efficient because agents can learn from what others are doing, from what they are exploring at each step. So it is more sample efficient if we consider the environment samples. It's also computationally cheaper because we only have one set of parameters to worry about and to update using backpropagation and so on. But we have the opposite problem where we can only expect homogeneous behaviors to be learned. There are some minor tricks to change that, but it doesn't change the fact that the representational capacity of just one neural network is limited and won't learn to do totally different and independent things. And that's where shared experience actor credit comes in, and it's just an algorithm that allows for each agent to have its own policy, but the experience to be shared among the agents. And that allows us to allows for distinct behaviors to be learned, because each agent can have its own policy. Each agent can have a distinct neural network. And it's also sample efficient, because agents can learn from what others are doing, because we have a way to share the experience. Of course, the fact that we still have a large number of parameters remain, but because this algorithm is quite sample efficient, that turns out not to be a huge problem if we compare it to the other solutions. So just to give you an intuition about a high-level idea of what we do, consider this grid wall on the right, where there are two agents that have to simultaneously go to the gray box in the middle. And they will only receive a reward if they go there at the same moment. And let's say we give them a reward of 1, and otherwise we give them a reward of 0. So in this task, it's actually quite hard. Even in this small grid wall, it's quite hard to get any rewards. And we want that whenever a reward is actually found, to make the most out of it. And say, for example, we have the standard independent reinforcement learning with no parameter sharing, for example, and we try to update the blue agent on the top. Traditionally, we would use the agent's experience, and whenever a trajectory is collected, we would update the agent's policy. With shared experience actor critic, we also reuse the observation of the other agent as if it were observed locally. However, we do some important sampling to correct for the fact that this was not actually collected by the right policy, by the policy we are updating, and then we are updating with both trajectories, and that can scale to a large number of agents as well. So we've tested this in a variety of tasks. Many of them were already explained by Jorgos before, but we focused in sparse rewards, and I think that's the most important thing, that shared experience actor critic works well with sparse rewards. And and we observed quite a good performance when doing that. So here I won't focus too much on the results, but the green one is shared experience actor critic, and it's on top. And not only does it learn faster than our baselines, for example, in less sample and environment samples than, for example, no parameter sharing, but it also converges to a higher return. And those are the plots for the robotic warehouse. But we also observe similar things in StarCraft, in level-based foraging, and in the sparse predator-prey. And yeah, I think the fact that it converges to higher returns is the most interesting aspect of this. And we were also able to compare it with other algorithms in the same tasks like QMix and MATPG, and also show this a similar trend. So just I have one more slide for some follow-up work that we did. It was in ICML 2021, so about a year ago, and it was called Scaling Multi-Agent RL with Selective Parameter Sharing. And it doesn't solve exactly the same problem that shared experience actor critic does. It mostly focuses on scaling to a large number of agents, especially when the behaviors that are expected are not homogeneous. So we don't really expect from all agents to do the same thing, and it's still a form of parameter sharing. That's why I placed it a bit on the parameter sharing side. And it still allows for distinct behaviors to be learned when needed, and it's sample efficient, but it does solve a slightly different problem and doesn't focus so much on sparse rewards. And that's all for me, and I'll hand over to Sean for the final presentation.
Okay, thanks, Phillips. And hi, everyone. I'm Sean. In the next few slides, I will introduce our work on emergent communication. Expressivity of emergent languages is a trade-off between contextual complexity and unpredictability. So there's some lag between my click. Yeah, here it is. So why do we care about emergent communication in our group? As mentioned by Stefano before, one way for the multi-agent systems to coordinate is through intercommunication between agents. And we would call those communication protocols negotiated by the agents during the learning to complete tasks as emergent communication, since there is no supervision for how to communicate. And when the communication channels are discrete or symbolic, we then refer those protocols as emergent languages. And here is an example from the speaker-listener environment implemented in the ePAML benchmark. In this environment, there are basically two agents, a speaker and a listener. And the task for the agents is to achieve some goal position. And the speaker knows which is the goal, but it cannot move. And on the other hand, the listener can move, but doesn't know where is the goal. So the two agents have to coordinate and communicate in order to complete this task. And of course, one way to do so, as shown in this diagram, is that the speaker can send a message to the listener saying that, go to t-shirt. So it tells the listener where is the goal. And in this example, the listener can then interpret the meaning of the message t-shirt as the object in the top left corner. And given this setup, an emergent language can be defined as a mapping function from meanings, that is the goals in our environment, to the messages. However, in this work, we wonder how well can these emergent languages work across environments. So here is an example. In the left environment, we have a cup and a car as distractors. So only one object in the environment matches with the message t-shirt. That is the t-shirt in the top left corner. But in the right environment, the two distractors are also t-shirts. So in this case, the listener might be confused by the message t-shirt since it is highly ambiguous. So a better language or better protocol in the right environment could be something like blue striped t-shirt. So is this ambiguous? So we ask two questions in this work. First, how to measure the ability of a language working across various environments. And we refer such ability as expressivity of emergent languages. And further, what determines the expressivity of emergent languages? We hope that the answer to this question could also help us to design environments that can facilitate more universally useful emergent languages. An intuitive answer to the first question could be mutual information. But unfortunately, in our work, we showed that mutual information is actually insufficient to capture this ability of working across environments. And instead, we follow an intuition from linguistics that is, if a language is more expressive, then its interpretation should be less dependent on the context, and it should be more able to work in all kinds of tasks. And also, by the way, the context in this work is defined as the target plus the distractors. And to be honest, some direct measure of this quantity is quite tricky. So in this work, we instead focus on the partial ordering between the expressivity, and we propose a definition of it. That is, given a set of environments and two emergent languages, if emergent language A performs better than the other B on some environments, while they perform approximately the same in all the remaining environments, when then say expressivity of A is greater than B. So this is quite similar to the setup of the transfer learning. To answer our second question, we then hypothesized that expressivity of emergent languages is actually a trade-off between the complexity and unpredictability of context in language games or in environments. So following this hypothesis, we can make 3 predictions if the meaning space is limited and fixed. So first, unilateral increment of contextual complexity should increase the expressivity. And similarly, unilateral increment of unpredictability can also increase the expressivity. And lastly, if we can't increase both both factors at the same time, then some moderate complexity and unpredictability should lead to the highest expressivity, which shows the trade-off effect between the 2 factors. So now I'm going to show you some examples about these 2 factors, complexity and unpredictability. So here is an example about the complexity of context. So in this diagram, there are 2 contexts. The top one consists of our target, that is the blue striped t-shirt, and a cup plus a car as distractors. In the bottom one, whereas the context consists of our target and a white plus a blue t-shirt as distractors. So as you can imagine, in the bottom case, we may prefer to encode more information about our target t-shirt into the message, since the other 2 are very similar to our target. So this leads to our definition of the complexity, that is the expectation of the probability that a context contains an object whose similarity degree to the target is less than or equal to some certain value. And of course, the metric for similarity may vary in different environments. And here is an example to illustrate the unpredictability of contexts. So in this diagram, there are 2 sequences of contexts. In the left sequence, we first have a yellow cup, then a white cup, then a green cup as distractors. So it's likely that we will have another cup as the distractor in the future. However, in the right sequence, we first have a white t-shirt, then a car, then a cup. So we would become more uncertain about what we will see in the future. And in this case, we may prefer to encode more information about our target into the message as well, in order to guarantee the success of the future trials. So this leads to our definition of the unpredictability, that is, the expectation of the ratio of candidates in the current context that are not in the in the context of previous ones. And to verify our trade-off hypothesis, we run 3 experiments. In the first experiment, we fixed the unpredictability of context across environments, and we showed that higher complexity leads to higher expressivity. So the languages from more complex contexts indeed work better on all types of tasks. And similarly, in our second experiment, we fixed the complexity and showed that higher unpredictability can lead to higher expressivity. And in our last experiment, we fixed the size of the meaning space, so the 2 factors cannot be increased at the same time. And in this case, we found that some moderate complexity and unpredictability indeed leads the best expressivity. And we also run our experiments across different environment setups, including larger channel capacity, larger agent capacity, and both larger channel and agent capacity. And all the 3 experimental results are consistent across different setups. So overall, in this work, we first proposed a measure of expressivity based on the partial ordering between emergent languages in terms of their generalization performance across environments. We also proposed and verified that the trade-off hypothesis about the determining factors of expressivity, that is contextual complexity and unpredictability. So yeah, that's all. Thanks. Now I guess I will hand over back to Stefano.
Yeah, thanks, Sean. Thanks everyone for doing your presentations. I'm glad this worked well. So this brings us to the end of the presentation. Thank you all for being here at the talk, for your time. Hope you found this interesting. Just a reminder about the resources I told you about earlier. So do check out our website, which you see here. Follow us on Twitter if you want to get updates also about the book when it comes out. And maybe we have a few minutes now to take some questions, which we'd be happy to discuss. So thank you again for the invitation.